Welcome to our presentation today. This presentation summarizes the findings and results in the paper Creating Artificial Modalities to Solve RGB Liveness by researchers from Vision Labs. My name is Cathie, and I'm an AI consultant at MarkTech Post. So what is face anti-spoofing? Basically, it's a technique or technology that distinguishes between fake or artificial faces versus a real person. And there's a growing need and growing integration of face recognition systems to our daily lives. For example, there are more and more biometric payment methods. And for high security large corporations, there's also a need for physical access control. The status quo of this technology uses RGB, red, green, blue, stream from colored photos with additional modalities such as infrared, depth, or thermal images. The problem with this is it requires extra sensors and extra hardware, which makes the RGB-only problem very important because establishments that have already placed RGB cameras are unlikely to change all their hardware, and hence we will have to work with RGB photos or videos only. Researchers in this paper utilized this dataset for which is the largest available face anti-spoofing dataset in terms of subjects, ethnicities, and fake types. So on the left, we have 4 types of sample data that is available in this dataset. The first row would be a bona fide real training data, and the second row is a bona fide testing data, which the researchers would test their classifier on. And the third row and the fourth row are both fake data. So in the training data set, we have mostly replay attack, which means it's the same artificial face, just rotating and replaying in different frames. And there's also a printed attack fake face in the test set, which just means that the same frame or the same image just get posted over and over again. This paper proposed the method of artificial modalities, and they proposed 2 new modalities that can be extracted from current data to provide extra information for machine learning. So the first modality, the optical flow, and it's based on the Liu et al. Paper, and they obtained an optical flow from 2 pairs. It will be the first and the last images from the track, and also the first and the second track images. The motivation behind that is that the flow for real track would change at different times, but the flow for fixed track should remain about the same. And the flow for bona fide track should also roughly show the 3D structure of movable face parts, for example, the eyes or the mouth. And in short, basically the optical flow modality track the delta or track the changes over the track. Another modality that the researchers introduced, rank pooling modality. It encodes video sequences into a feature factor using SVR, developed by Fernando et al. There's a regularization hyperparameter in this model that needs to be chosen, and the researchers here chosen C equals 1, which preserves identity info, and C equals 1000, which will contain face shape changing along the track. Moreover, there's also a need of data augmentation because there's a huge difference between the so-called replay fakes versus printed fakes. So given a track, the researchers create a new one by replicating just a random image out of the track and change the track label to fake. This enables the researchers to create a new family of fake tracks that looks like printed fakes and will help them to train the system. Last but not least, the researchers also uses SimpleNet, which is a combination of convolution filters, batch normalization, rectified linear units, and max pooling to build their model. Here is the grand architecture that the researchers end up using. On the left is the artificial modalities, in the middle is the SimpleNet that we briefly mentioned, and there are more pooling layers until the final classification goal is reached. To evaluate the performance of this model, due to imbalanced samples, an average classification error rate needs to be used, and it's basically the average between the attack presentation classification error rate and the bona fide presentation classification error rate. The results these researchers were able to achieve were simply amazing. By comparing it with the baseline error rate, which used just the SimpleNet at around 20%, by adding all these artificial modalities plus data augmentation, they were able to achieve an error rate as low as 2.72%. So what have we learned from this paper? The researchers have demonstrated that they can solve the face anti-spoofing problem through creating artificial modalities and through data augmentation. Rank pooling with different regularization parameters, together with optical flow, can decrease the risk of overfitting. And they have also demonstrated that a simple augmentation trick can enrich the collection of their samples. enabling them to get first place in this attack detection challenge in 2020.